Hey guys, this is 14.4, and in this section, conceptually what we want to talk about is trying to solve trigonometric equations. And so I might have an equation like sine squared of x equals, let's say 1/2. Okay, for me to solve this, I kind of want to get rid of this square root, or get rid of this square, so I'm going to have to square root, which produces a plus or minus. So now I have not sine squared, but just regular old sine of x equals plus or minus root 1, which is 1 over root 2, which is actually equal to root 2 over 2. If you remember the rule of pulling roots up and leaving the inside behind, with plus or minus root 2. Alright, so if I were to just think about this, ignore the middle here, the sine of x equaling positive or negative root 2 over 2. If I were to look for places where this is true, and I think about my sine wave, my sine curve, right, it looks like this. Okay, here's 1, right, 1, and here's negative 1. Well, root 2 over 2 is 0.707, so it would be like right around here. And I'd have a dot there, I'd have a dot there, I'd have a dot there, I'd have a dot there. And that's on the positive side. On the negative side, it's about here. So I'd have a dot there, I'd have a dot there, I'd have a dot there, I'd have a dot there. And this would continue in perpetuity, forever. As I keep going through this graph forever, we would recognize, hey, you keep bumping into more and more of these answers. And so when we go through and solve this, we need to distinguish between, do we want answers that only exist in the first cycle of the wave, that would be from 0 to 2 pi, or do we want to know all of the answers for forever, which technically there's infinitely many, so that's a little bit hard to write all of the answers. I'd never be able to finish, so we have to find shorthand or shortcut ways to write all of these places that are true. And so we want to, this is what we're after. We're trying to figure out when is a curve equal to a set value, and then based on that be able to tell, are we talking about all of the values or just some of them. There's going to be using some of our algebra skills that we've used all year long. We're trying to piece all that stuff together. So I'm going to go through about 4 examples. This will be a little bit of a longer video because of that. I'm going to go through 4 examples of solving these, and I'm going to reference the unit circle quite a bit to help make this pretty seamless. Okay, we're going to start here with questions 9 through 14. In these questions, we're doing a really simple solve. Okay, let's take a look at question number 10. As we do question number 10, keep in mind that in this section we're being asked to find the general solution. General solution means not just the first cycle of answers, but all of the answers. And so we're going to have to be thoughtful of that as we finish. Okay, and so where is my mouse? There we go. Okay, so we're going to take number 10, which is one of the more challenging questions. At least it has a hiccup in it that's kind of worth talking about. Root 3 cosecant of x plus 2 equals 0. So for me to solve for x, what I want to do is I want to isolate the trig function. So in this problem, I'm going to minus 2. Pretty straightforward. I have root 3 cosecant of x equal to negative 2. Next thing would be to divide by root 3. Divide by root 3. Now right now we have a root in the bottom, and that's not great, but hold on. See, the cosecant isn't a function that I actually know how to solve real well, but I do know how to work with its reciprocal. If you remember, cosecant is equal to 1 over sine. And since that's equal to negative 2 over root 3, if I flip this fraction upside down, I will have to also flip this fraction upside down. So in order to put sine on top, which is what I want to talk about the sine of x. It equals negative root 3 over 2. At this point, I need to get rid of the sine function. We can use the arc sine to do that, or the sine inverse rather. For most of you guys will remember the sine inverse. Now I can do that in my calculator and the calculator will give me an answer. But we're supposed to answer this in radians. I don't understand the radian decimals out of the calculator. I'm going to have to do it in degrees and then convert. I think we'd be better off if we just look at the unit circle. Keep in mind, we're looking for places when the sign, which is the y value, is negative root 3 over 2. So if I jump back here into chapter 13, I look at my unit circle. I'm looking for places where the y value is negative, so that's going to be on the bottom, and I want it to be negative root 3 over 2. There's one, and there's another one. So my two answers are going to be at 4 pi over 3 and at 5 pi over 3. So let's go back to here. We're going to say that x, oh goodness, Mr. Welch. We're going to say that x would equal 4 pi over 3, and underneath it I'm going to write or 5 pi over 3. Now those are two specific answers from the circle. Where this says to do the general form, that would mean that I could keep going around the circle over and over and over again. And every time I come to those two places, I still want to count them. The way we're going to do that in shortcut or shorthand is we're going to add 2 pi, that's a circle, and then we're going to put an n with it. N could be any number of times. It could be 1 time, 2 times, 3 times. N is the number of times we're going to go around the circle. Same thing here, plus 2 pi n. So in both of these problems, both answers, we're going to say, okay, 4 pi over 3 is the first one you're going to run into, but if you removed 1 full circle or 2 full circles or any number, a whole number of full circles around, you'd land right back where you are. That is true for sine and cosine because 2 pi is the period, which is a cycle, right? If you do a tangent, so this is the answer for our problem. If you did a tangent, right, like number 14, you would add pi n. You notice it right here, right, n pi or pi n. In these problems, because tangent cycle is only 1 pi over b, we would use pi times n instead of 2 pi. All right, so that's the first example of doing general form. In the next type of problem, which is questions 16 through 21, notice that it doesn't say in general. It says in the interval from 0 to 2 pi. That means all of our answers should come from the unit circle. Okay. Well, let's take a look at let's do number, we did sine, let's do a cosine. Wait, did we do cosine on that? Yeah, we did cosecant, which was a sine. Let's do a cosine. Let's look at number 18. So number 18 has 3 cosine of x equals cosine of x minus 1. In order for me to solve this, I need to get all my cosines together so that I can isolate my cosine. So I need to move this cosine over. I cannot divide it. I can only add or subtract it. Minus cosine of x. Over here, cosine minus cosine is 0. I end up with negative 1 on the right equals. Now if I take 3 cosines and I minus 1 cosine, I should have 2 cosine of x. And to finish this, I'll divide by 2. So now I'm wondering, when is the cosine of x equal to negative 1/2? I could take the cosine inverse, but again, I'm going to fight with the radians and degree versions. So I'm just going to go to my unit circle and look for when is cosine equal to negative 1/2. Well, cosine is the x-coordinate. X-coordinates are negative on the left, so there's a negative 1/2. And I think right here, there's another negative 1/2. So that would give me values of 2 pi over 3 and 4 pi over 3. But because I'm looking for just answers between 0 and 2 pi, my answers to this question would be 2 pi over 3, comma, and we said 4 pi over 3. I don't need the plus 2 pi n because I'm not doing the general form. I'm just doing the form of the answer that's on one side or the other. These others, let's see if we can take a look. You know, some special cases there. that I think is going to be at the heart of what you need to understand to be able to move forward. Really, 9 through 21 are really at the heart of what's the basics of what we're doing. As you get further into the assignment, if you have more questions, come in and see me. Let's discuss the situation that you're looking at. Good luck. Hopefully that's enough to kind of get you going, get the ball rolling, and we'll see you guys in class.